All right, on to the fun stuff. Newton's second law in component form, using the sigma sign. Haven't we done this already? The net force in x equals the stuff that makes it go in the x direction minus the stuff that holds it back in the x direction equals mass times acceleration in the x direction. For the net force in the y direction, stuff that makes it go in the y direction minus stuff that holds it back in the y direction equals mass times acceleration in the y direction. Newton's laws can be reduced to the following two rules. Forces that are perpendicular to the acceleration vector will cancel each other out. Forces that are parallel to the acceleration vector will add to the net force, ma. But if the force is opposite to the acceleration vector, we're going to count that force as negative. Show this concept in the following three situations. Assume there is friction in the first two. All right, so if we're dealing with friction, that's a force. Whenever we have a force, we need to start with a free body diagram. So let's go ahead and draw ourselves a nice free body diagram to get us started. We have the downward weight force, so there's our mg. Then we have the perpendicular to the surface normal force. This box would slide down, so that means friction is going to go in this direction. And that's it, as far as our forces go. Now, we have to resolve mg into its components because it is neither parallel nor perpendicular to the acceleration. We know the acceleration is going to be down the ramp. So mg is not parallel or perpendicular, so we're going to resolve it into its components. To draw that triangle, first thing I like to do is just continue on my normal force vector until it's equal and opposite, and then just connect it to the weight vector. So now I have this nice triangle, and here's my angle right here. There's my theta. Same theta as this. I know this side is touching, so this is my adjacent side, and I know this side is opposite, so this is my opposite side. So this is going to be mg sine theta, and this is going to be mg cosine theta. Okay, so just from this I can tell my normal force is equal to mg cosine theta, and then my frictional force would be mu times mg cosine theta. My acceleration going down the ramp is going to be mg sine theta, but that's not what we're doing for this one. All we're doing is we're looking at the parallel equation. So this mg sine theta here, what I would call that is the parallel component of your weight force. Meanwhile, this one up here you could call your perpendicular component of your weight force. So that way we can put this into a nice, neat equation. So the stuff that makes it go minus the stuff that holds it back, parallel. And that parallel just means the direction of the ramp, or parallel to acceleration, to be a little bit more consistent. So parallel to acceleration, stuff that makes it go. What's going to make it go down the ramp? It's going to be that parallel weight force minus the stuff that holds it back, our frictional force. And all of that is going to equal mass times acceleration, whatever your acceleration is from this. Perpendicular, stuff that makes it go. Well, we're not sinking into this ramp and we're not floating above it, so we're just going to say up is positive. So that would be our normal force minus our perpendicular component of the weight force equals mass times acceleration. And all of that, of course, equals 0. As I said, we're not sinking, we're not going. So then our normal force will equal perpendicular weight force, which is mg cosine theta. On to the next one. Again, starting with a free body diagram. We're talking about forces. So we always start with a free body diagram. We have mg. We have this tension at this angle, whatever that is. We have a normal force. Whoa, way too big, Mr. Scopetis. Our normal force is not going to be the same size as our weight force because we're also having to deal with this upward component of this tension. And then we also have friction in this direction. FF, Fn. Parallel. Obviously, our acceleration is going to be in this direction. So Ft is not parallel or perpendicular, so we're going to resolve it into components. So we have parallel component and perpendicular component. There's our theta. This is our adjacent, so we're going to call this Ft parallel, and then this will be Ft perpendicular. All right, so parallel. Stuff that makes it go is going to be parallel component of our tension minus the stuff that's holding it back, FF, equals MA. Yikes. Equals MA. For the perpendicular equation, we have up minus down, so Ft perpendicular minus mg equals 0 because we're not going up or down. So Ft perpendicular, if you want to simplify this a little bit more, will just equal mg. Finally, we have this hula hoop attached to a string, and we're pulling this hula hoop along with this angle to the vertical. So let's say it's not a hula hoop. Let's say it's a bowling ball attached to a string or something massive that'll have a weight that goes down and then a tension that's going to go in this direction. And it's going to make some angle with the vertical. So what direction is our acceleration? It's going to be exactly to the right. Ft is not parallel or perpendicular, so we have to resolve Ft into its components. So we have this Ft parallel, and then we have this Ft perpendicular. Parallel equation. Stuff that makes it go minus the stuff that holds it back. Ft parallel minus nothing because there's no friction here. There has to be friction if it's rolling, but we'll deal with that sometime later. Equals mass times acceleration. And then in the perpendicular, we have stuff that makes it go, so we'll say up Ft perpendicular equals mg. If we do stuff that makes it go minus stuff that holds it back equals 0, then we solve for mg, we get this equation. So that's it for those test your understandings. Let's press on.